For over a century, physicists have tried to understand the physical properties of objects at the subatomic level, also known as quantum mechanics. Some of the greatest minds like Einstein, Heisenberg, and Niels Bohr have tried their hands at it. Because quantum mechanics was hard to understand and seemingly irrational, Erwin Schrödinger kind of made a popular quantum mechanics for dummies thought experiment that is now known as Schrödinger's cat. This experiment consisted of a closed steel container, a cat, and a radioactive poison that will detonate randomly. Now, because we do not know whether the poison has detonated, we can think of the cat as being both alive and dead until we actually open the box to observe it. This attribute of being in two different states at once until measured is called superposition, and it's a characteristic feature of subatomic particles like electrons and photons. Now, while classic computers mimic humans in the way that we carry out calculations using bits of ones and zeros as data, quantum computers like Sycamore mimic nature using quantum bits or qubits of both 1 and 0 as data. These qubits can exist in both states of data at once and change accordingly to give the required answer for a task. And this also means that compared to bits, qubits process a ridiculous amount of information faster. And this ability to process more information faster increases as you increase both the bits of a classical computer and qubits of a quantum computer like Google's Sycamore. For instance, unlike 2 classical bits that will exist in either of the 4 states, 2 qubits can exist in all 4 states at once, 3 qubits in 8 states, 4 in 16, and so on. The qubits in the circuit are entangled in such a way that this helps the computer affect the changes across all the qubits to arrive at the correct state that generates the solution to your task. This behavior is also derived from quantum mechanics and was described by Einstein as spukhaft Fernwirken, or spooky action at a distance. This is the effect where 2 particles are correlated with each other in such a way that you can actually predict the properties and behavior of any one of the particles just using one of them, no matter how far apart they are from each other.
In reality, the kinds of calculations and problems solved by these quantum computers and processors are seldom translated to real-life applications. This means these types of problems are extremely specialized, and as such, quantum computers will not be replacing their binary classical computer predecessors anytime soon. So far, these quantum computers have been built to solve certain types of problems. As of now, the exploitation of quantum computing has only reached a point where there are a number of significant obstacles that may stand in the way.